This is an introduction to digital control systems. Subsequent videos will cover several areas in digital controls. They include just describing computer-based control systems. That's really the topic for this video. We'll look at sampled data, being able to transform between the S domain and the Z domain using the relation that Z is equal to e to the st. We're going to examine the Z transform in another video and use that to analyze the stability and time response of a discrete system. And we'll also look at analysis and design of digital control systems, actually coming up with our own and checking on the stability of these control systems. First of all, the difference between implementing continuous and digital control systems. Here's an example of a PID compensator in the continuous domain. The values of these components, resistors and capacitors, determine the gains for our PID compensator. So we have capacitors, resistors, and an op-amp. In the digital domain, this would be replaced with a computer, and that has some advantages. One being reduced cost, meaning that a computer can provide a compensation for multiple systems. So out of one computer you can get many controllers. Flexibility, in that changing the gain value for a compensator just requires a change in code rather than swapping out components. And less variation. With a digital control system, we wouldn't have to worry about component tolerances or thermal characteristics. Here's a block diagram representing a digital controller. A computer typically takes the place of a cascade compensator, so you can see that here in this feedback diagram. Digital computer provides a signal to the plant. And expanding this block a little bit, we see that there's often, well, let me go down here. We have these signals R, E, F, and C, and they can be either analog or digital. It's common for the input and output of the plant to be analog, so a continuous signal, and in that case we would need an analog to digital converter going into the digital computer and a digital to analog converter between the computer and the plant. Digital to analog conversion is a nearly instantaneous process. Here's a schematic representing a 3-bit digital to analog conversion. So this analog output could have values between 0 and 7 volts. This switch represents the least significant bit of our digital value, and this is the most significant bit. So if we wanted 1 volt, this switch would be closed. We'd have 1 volt times 1 volt plus 0, give us output of 1. If we wanted 5 volts, then we'd have this switch closed and this switch closed. So we'd have 1 volt plus 4 volts to give us 5 volts. And if all three were closed, then we'd have 7 volts. Like I said, this is a nearly instantaneous process, so we're going to ignore the effects of digital to analog conversion in our system analysis. On the other hand, analog to digital conversion, as described in this figure, uses multiple steps, and so it introduces a delay. And that delay we have to account for in our modeling. This chart shows a continuous time signal, f of t, and here's time on the horizontal axis, and then we're converting that to a 3-bit signal. So these are our different digital values. Now we're going to sample this signal at 2 Hertz. So twice per second we're going to sample a new value. And what happens is that in this figure the value is sampled, and then that value is held until the next sampling interval. And then we sample it again and we hold that new value. So the conversion goes from the smooth curve to a stair-step looking curve. And this plot just shows the digital values that you get in binary. So in decimal we have 0, 3, 4, 5, 5, 6, 6, 6, 6, 6, 6, 6 as time goes on. There's also a quantization error, and that refers to the fact that the analog signal could vary some, but the discrete signal would not change at all. So there's some quantization error, some round-off error, if you will. Now we need to model this analog to digital conversion, or sampling, and so the way that we represent this is with an ideal sampler, which takes us from a continuous time signal to a sample time signal, and the notation for those are f of t and f star of t. So here is our continuous time signal, and here is a sample time signal. We have the original value times the Dirac delta function. And then after the sampler we have a hold. So this is a sample and hold. And there are different types of holds, common one being the zero order hold, where it just holds the previous value until the next sampling time. This video has introduced the topics that we'll be covering in subsequent videos. We've looked at a little comparison between continuous and discrete time control systems, and we've looked at how digital computers as controllers often require conversion between analog and digital. And so we found that we're going to ignore the effects of a digital to analog conversion, but we will model the analog to digital conversion. And that mathematical model will be given in a subsequent video.